The classical definition of probability. Welcome, everyone. Let's begin our lesson on the classical definition of probability. To start, I want to remind you of what we covered in our previous subsection, where we discussed the concept of equally likely outcomes. This is a crucial starting point. You see, this idea of outcomes having the same chance of occurring is the very foundation upon which the theoretical, or what we often call the classical approach to probability, is built. Now, here is the key takeaway for today. When we can safely assume that every possible outcome of an experiment has the exact same chance of occurring, we don't have to rely on guesswork. Instead, we can use a formal mathematical formula to precisely determine the probability of a specific event. In the next few slides, I will show you exactly what that formula looks like and how to apply it step by step. Understanding the terminology. First, we have the term random experiment. Now, don't let the word experiment intimidate you. In mathematics, a random experiment is simply any action or process that results in one of several possible outcomes, where we cannot predict the exact result with absolute certainty before it happens. Think of something as simple as tossing a coin or drawing a single card from a deck. We know what could happen, but we don't know exactly what will happen until the action is complete. Next, we need to define what an event, which we denote with the capital letter E, actually is. An event is a specific outcome, or perhaps a collection of outcomes, that we are specifically interested in studying. To put this into perspective, let's look at the experiment of rolling a die. While the die could land on any number from 1 to 6, if we decide we are only looking for getting an even number, then that specific group of outcomes, 2, 4, and 6, is what we call our event. Now that we've established that the classical approach relies on the idea of equally likely outcomes, let's take a moment to master the specific vocabulary you'll need to navigate these problems. Understanding these two building blocks, the experiment itself and the specific event we are tracking, is crucial, because in the next slide, we are going to see how we use them together in a formal mathematical formula. The formal definition. As we touched upon in our first slide, the classical definition of probability gives us a precise mathematical method to calculate the likelihood of an event. Let's call it event E, occurring. However, there is one crucial condition you must always remember. This method only works provided that all the possible outcomes of your experiment are equally likely to happen. So, how do we actually write this down mathematically? The probability of an event E, which we denote as P of E, is defined as the number of outcomes favorable to E, divided by the number of all possible outcomes of the experiment. Now, that sounds a bit wordy, doesn't it? To make it much easier to work with during your calculations, you can simplify that thought process. Just think of it as a simple fraction. P of E equals the number of favorable outcomes over the total possible outcomes. Now that we have established the basic terminology, understanding what a random experiment is and what we mean by an event, let's move on to the heart of today's lesson, the formal definition. In the next few slides, we are going to walk through a step-by-step process to help you apply this formula correctly, and then we will look at some real-world examples, like rolling dice and drawing balls from a bag, to see this formula in action. Step-by-step process to calculate probability. First, you need to identify the sample space. This means you should start by listing every single possible outcome that could happen in your experiment. Once you have that list, count them up. This count will become your total possible outcomes, which, as we saw in the formula on the previous slide, will serve as your denominator. Second, identify the favorable outcomes. Now, look closely at the specific event, which we denote as E. You need to scan through your sample space and pick out only the outcomes that satisfy the specific condition mentioned in the problem. Count these specific outcomes to find the number of outcomes favorable to E. This number will be your numerator. Third, apply the formula. This is where you bring everything together. Take the number of favorable outcomes you just found and divide it by the total number of possible outcomes. Finally, simplify. Once you have your fraction, always check if you can reduce it to its simplest form. This makes your final answer much cleaner and easier to interpret. Now that we understand the terminology and the formal definition, let's break down how you can actually apply this to solve any problem. I want you to follow this consistent 4-step process to ensure you don't miss anything. We will practice this exact step-by-step method in the next few slides with some real-world examples. Real-world examples. Now that we have understood the theory and the 4-step process, let's put it into practice with our first concrete example. Take a look at example 1, which involves rolling a fair die. Here is our scenario. We are rolling a standard 6-sided die exactly once, and our goal is to determine the probability that the number facing up is a prime number. To solve this, we will follow the 4 steps we just discussed on the previous slide. First, step 1, we need to identify the sample space, which means finding the total possible outcomes. When you roll a die, you could land on a 1, a 2, a 3, a 4, a 5, or a 6. So, our set of possible outcomes is 1, 2, 3, 4, 5, and 6. If we count them up, the total number of outcomes equals 6. Next, step 2, we need to identify the favorable outcomes. Remember, our specific event, which we call E, is getting a prime number. Looking at our list from step 1, we need to pick out only the prime numbers. Those would be 2, 3, and 5, so the number of favorable outcomes is 3. Now for step 3, we apply the formal formula we learned earlier. We take the number of favorable outcomes and divide it by the total number of possible outcomes. This gives us the probability of E, which is 3 over 6. Finally, step 4, we must always simplify our result. Since 3 is exactly half of 6, we can reduce the fraction 3 over 6 down to 1 over 2. So the final probability of rolling a prime number is 1/2. This makes sense, doesn't it? Half of the numbers on the die are prime, and half are not. Now, let's try a slightly different scenario with a bag of colored balls in the next example. Real-world examples continued. Now that we've mastered the concept of rolling a die in our first example, let's try something slightly different to see if you can apply the same logic to a different type of experiment. Let's look at example 2, which involves drawing a ball from a bag. In this scenario, we have a bag containing 5 red balls, 8 white balls, and 4 green balls. We are going to draw just one ball at random, and our goal is to find the probability that the ball we pick is white. To solve this, we'll follow the exact same 4-step process we just practiced. Step 1, we need to find the total possible outcomes. Remember, the total outcomes represent our entire sample space. To find this, we simply add all the balls in the bag together, 5 plus 8 plus 4, which gives us a total of 17. So our total number of outcomes is 17. Step 2, now we identify the outcomes favorable to our event. In this case, our event, which we'll call E, is drawing a white ball. Looking at our data, we can see there are exactly 8 white balls. Therefore, the number of favorable outcomes is 8. Step 3, now we apply the formal formula we learned on the previous slides. We take our number of favorable outcomes and divide it by our total possible outcomes. This gives us the probability of E, which is 8 over 17. Finally, step 4, we check if we can simplify the fraction. Since 17 is a prime number and doesn't share any common factors with 8, this fraction is already in its simplest form. So, our final answer is 8 over 17. It's the same logic as the die roll, just with a larger set of possibilities. As we move to the next slide, I want you to keep an eye out for some common pitfalls that might trip you up when working with these types of problems. Common mistakes to avoid. First, please be careful not to ignore the equally likely condition. As we discussed in our very first slide, this entire classical approach is built on the assumption that every outcome has the same chance of occurring. If you're dealing with a weighted or biased die, where certain numbers are more likely to appear than others, the formula we just practiced in our examples simply won't work. Always check if the outcomes are truly fair before you begin your calculations. Second, a very common mistake is confusing your favorable outcomes with your total outcomes. I often see students accidentally invert the fraction, putting the larger number on top. To avoid this, always remember, the total number of outcomes must go in the denominator, which is the bottom of the fraction, and the favorable outcomes, the specific part you are looking for, must go in the numerator, which is the top. Finally, watch out for errors when identifying your sample space. When you are listing all possible outcomes, be meticulous. Ensure you have listed every single possibility without skipping any, and importantly, do not include any duplicates. If your total count is off at the very beginning, your entire probability calculation will be incorrect. Now, before we wrap up our lesson and look at the final summary, I want to pause and discuss some common pitfalls. Even when you understand the formula, it is very easy to make small errors that lead to incorrect answers. Keep these tips in mind as we move to our final slide for the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before we wrap up. First and foremost, remember that the classical definition of probability is a specific tool. It is only valid to use when we can assume that all possible outcomes of an experiment are equally likely. If the outcomes are biased or weighted, as we discussed in our common mistakes slide, this formula won't apply. Second, keep the core formula at the front of your mind. The probability of an event, which we denote as P of E, is calculated by taking the number of favorable outcomes and dividing them by the total number of possible outcomes. Third, keep in mind how we present our final answers. Probability is essentially a ratio, so it is most commonly expressed as a fraction. However, depending on what your question asks for, you can also represent this value as a decimal or even a percentage. Finally, if you ever feel stuck on a problem, just follow the systematic process we practiced in our examples. Always start by identifying your entire sample space, that is, every possible outcome. Once you have that total, you can then isolate and count only the specific outcomes that satisfy the conditions of your event. If you follow these steps and keep an eye out for those common pitfalls, you'll find that calculating probability becomes much more straightforward. Great job today!